Hello, and welcome to Game Theory. I'm Professor Naomi Utkoff of the United States Naval Academy. In this video, we'll introduce an incomplete information vaccination game and find its Bayesian Nash equilibrium. We'll amplify the two-player version of the vaccination game from video 23 by introducing private information about susceptibility. Two players simultaneously and independently decide whether to vaccinate against smallpox or not. Each player's type represents her chance of contracting smallpox if neither player vaccinates. Types are independently and uniformly distributed on the 0-1 interval. If at least one player vaccinates, neither gets sick. The vaccine costs 1 and smallpox costs 4. As we mentioned in the previous video, the approach we take to finding Bayesian Nash equilibrium depends on the structure of the action and type spaces. In this game, the type spaces are continuous and the action spaces are discrete. First, we show that each player's Bayesian Nash equilibrium strategy divides the type space into a vaccinate piece and a don't vaccinate piece. Second, we identify which types correspond to which action. The symmetry of the type distributions and payoff functions implies that the players adopt identical Bayesian Nash equilibrium strategies. We'll first explain why the Bayesian Nash equilibrium strategies must satisfy the structure in blue. The idea behind the structure of the strategy is that vaccinate is the expected utility maximizing action if a player is sufficiently susceptible to smallpox, and otherwise the player should select don't vaccinate. If it makes sense for player I to vaccinate at some susceptibility Ti, it makes sense to vaccinate at all higher susceptibilities. Vaccination is a precautionary action to avoid smallpox, so ceasing to vaccinate as one's vulnerability goes up cannot be expected utility maximizing. There must be some dividing type T-bar over which a player vaccinates and under which a player does not. We now want to characterize this T-bar in terms of expected payoffs. We'll do this from player 1's point of view. The expected payoff of don't vaccinate decreases as type increases. At low types, the player picks don't vaccinate. At sufficiently high types, the expected payoff of don't vaccinate falls below the expected payoff of vaccinate, so the player picks vaccinate. Now we can write down expected payoffs and find T-bar. A player who vaccinates gets -1 for sure. We need to untangle some probabilities in the event that a player doesn't vaccinate. Here's player 1's expected payoff when she plays don't vaccinate. Players 1 and 2 adopt the same strategy, but neither knows the other's type. Therefore, from player 1's point of view, player 2 vaccinates whenever T2 is greater than or equal to T-bar, and does not vaccinate whenever T2 is less than T-bar. All types are equally likely under the uniform distribution. Therefore, the probability that player 2 vaccinates is 1 minus T-bar, and the probability that player 2 does not vaccinate is T-bar. If player 2 vaccinates, player 1 receives 0. If player 2 does not vaccinate, player 1 gets sick with probability T1, in which case she receives -4. We're left with -4 T-bar times T1. We argued in step 2 that T-bar is the type at which player 1 is indifferent between the two actions. Therefore, set T1 equal to T-bar and solve for the T-bar at which EU1 of V equals EU1 of D. T-bar equals 1/2. Here is our Bayesian Nash equilibrium. Regret is distinctly possible. If neither player vaccinates and one or both become sick, the sick players will regret their decision not to vaccinate. Thanks so much for watching this video about an incomplete information vaccination game and its Bayesian Nash equilibrium. In the next video, we'll discuss why people use auctions to buy and sell things and introduce several auction formats in preparation for our study of their equilibria.